Okay, this is the final talk of the session, and the speaker is Satada. He's a final year PhD student at Princeton University, advised by Jennifer Rexford. He works at the intersection of internet measurement and programmable networks, with a recent focus on applications to video conferencing and network security. Okay, he's on the job market for academic positions in the United States, Canada, and Europe. Okay, with that, Satada, please go ahead.
Thank you for the introduction. Just testing it out. All right, welcome everyone to the last talk of this session. Today I'm going to talk about how to scale video conferencing infrastructure to meet future demands using an SDN-inspired redesign and programmable data planes. This is joint work with Oliver, June, Ravi, and Jen. Video conferencing is an essential application across industries such as business, healthcare, and education. It exploded in growth in 2020 and continues to grow today. Over the past years, we have seen increasing adoption, with the number of users expected to grow to double in the next 5 years. Expectations in terms of higher video quality, low latency, and more number of participants in a single video call, like in a webinar. And complexity and heterogeneity in the types of devices and networks used. For example, cellular networks are more and more prevalent. And so these trends are very quickly outpacing the current technology and infrastructure. So in this study, we wanted to show how do we provide consistently high quality at scale. So when we think about video conferencing, we typically think about two friends or colleagues interacting across the internet, where media is captured on one side, it is transferred over the internet, and played back on the other side. However, modern video conferencing applications like Zoom actually deploy massive infrastructure in order to realize this kind of a video call. And this infrastructure is what actually enables multi-party calls across the world. Now, we observe that the prior work has focused a lot on the end users by, for example, developing video codecs, rate adaptation algorithms, and performing measurement studies. In this work, our focus is in the middle. It's on the role of the application operator and their infrastructure. And so we study this because their role has typically been underexplored so far. So at the cornerstone of modern video conferencing is essentially the selective forwarding unit, or an SFU. And this is used by major operators like Zoom, Google Meet, and open source implementations like MediaSoup. So the SFU has two major roles. One, it relays audio and video streams from one participant to all the others, and then across all the participants, as you can see here. The second role is essentially that the SFU monitors the network conditions at each user, and then adapts the media signals to match the capabilities of the network at each user. So in this case, as you can see, the pink participant has a lower network quality, and so the SFU adapts the signal to have a lower frame rate from 30 FPS to 15 FPS. Now, SFUs are notoriously hard to scale, and this is for two main reasons. One, the workload is actually really hard to predict. And apart from the diurnal variations that is typical, there is dynamicity even within a single meeting, because users join and leave, they share or unshare their media, and so on. The second reason for scalability being hard is that the work done by the SFU is actually dependent on the number of streams and not the number of participants. So therefore, the work scales quadratically with the number of participants. As you can see, when a fourth participant joins a three-party call, the number of streams actually goes up from 9 to 16. And so the SFUs have to handle, on one hand, the dynamic high-volume workload. And on the other hand is the fact that if application providers under-provision their resources, then that can massively affect quality. So today, operators are really left with two options. One, they can massively over-provision their infrastructure, which can be costly and wasteful, or they can reactively auto-scale in the cloud. And this can risk harming QoE for the users when the scaling is done. And we confirm this by running experiments with media soup on a powerful server, and we keep increasing the number of participants until we see that at some point, the quality metrics become so bad that essentially the conferencing call becomes unusable, as shown in red here. So in this work, we carefully analyze the SFU's workload and come up with this key insight, that SFU operation is strikingly similar to traditional packet processing. So the first role of the SFU, which is relaying audio and video streams, is similar to multicasting in standard networking parlance. And the second role, which is monitoring and adapting media signals, works something like this. So if you have a stream coming in from the blue user with frames labeled A and B, then for the pink user, when quality is being adapted, this clearly defined and labeled set of frames with A is not forwarded and B is selectively forwarded. So this selective forwarding is similar to what a firewall does in a network. And so, boosted by this observation, we designed Scallop. In designing Scallop, we essentially forego reactive approaches like new scaling algorithms and so on, and do a fundamental rethink of video conferencing infrastructure in order to support long-term traffic forecasts. Scallop is the first of its type hardware-software SFU co-design inspired by the principles of software-defined networking. And so naturally, Scallop has two parts. One is the software component, which handles critical but very infrequent tasks, and the hardware component, which really does the heavy lifting by relaying the high-volume media streams. And because of this intervention, we are able to offload 99% of the SFU's workload directly to hardware, which leads to us supporting up to 128,000 concurrent meetings in a single switch, which is a 10 to 200 times scale improvement over software SFUs at comparable cost, and also with a latency reduction by up to 27 times. But in order to do so, we had to solve several challenges. One, the SFUs written today are written as monolithic softwares. And so there is no clear delineation between the control plane and the data plane. Second, even though the replication is similar to multicasting, the actual multicast requirements are very different and much more complex. So compared to traditional IP multicast, here we have to not only replicate video frames, which can consist of multiple packets, we have to also selectively forward them. And third, we designed Scallop to be compatible with the widely deployed standard of WebRTC. And so WebRTC does not actually define an SFU, nor does it provide any guidance on how an SFU could be designed. And so the existing systems that use WebRTC typically implement a split proxy kind of design where packets are depacketized and repacketized as the SFU. So for our system to work, we had to figure out the right kind of proxy architecture for Scallop, the way to handle feedback semantics, and how to do transparent rate adaptation. And so these challenges together lead us to the following research questions. One, how do we disaggregate the work of the SFU into control and data planes? How do we first realize and then scale application layer multicast? And then third, how do we make Scallop interoperable with WebRTC? Now in this talk, due to time, I'm not going to talk about the third challenge, but I encourage you to read the paper for that. So I come to the solution to the first challenge, which is the SDN-inspired disaggregation. We did a thorough analysis of the SFU workload, and we found that it is amenable to a control and data plane split, which is our key insight here. So we found that there are three main classes of work that the SFU does. One, where the latency requirements are not super strict, And the event rate is every few minutes, for example, signaling and session management. The second class is where the latency requirement is a little bit stricter, and the event rate is roughly 2 to 3 per second. And so this is like handling feedback messages and so on. And finally is the actual work of replicating and forwarding the media packets, which is super latency critical, and the event rate is hundreds of packets per second. So to summarize, we can actually plot these 3 tasks across the following 3 axes. We see as we go down the list of tasks, we require lower and lower latency. The event rate becomes higher and higher, but thankfully for us, the tasks require lower and lower programmability. And so therefore, we are able to build this particular design. We have a controller, a switch agent, and a data plane. The data plane resides entirely in hardware, and the switch agent and the controller form a 2-tier control plane. And the switch agent actually lies within the switch itself, close to the data plane, while the controller can be centralized and can potentially coordinate with multiple switch agents. All right, with that, let me come to the solution to the second challenge, which is how do we first realize application layer multicast, and second, scale it up. So here, our key insight is that packet processing platforms already have native packet copying capabilities, and those can be leveraged for this style of replication. So in case of programmable switches, some of them have bulk packet copying capabilities. For example, the Intel Tofino has a traffic manager where it also has a packet replication engine. For other platforms like SmartNICs and GPUs, either they do not have bulk replication capabilities or they do not yet expose it. And so, for example, in the NVIDIA BlueField 3, we use the mirroring construct, which is used for telemetry operations in order to achieve this kind of multicasting. And so here, I'm not going to talk about the SmartNIC implementation. I implore you to check out the paper. So let me talk about the solution using the Tofino. So before going there, let me give you a bit of a background on the Tofino's packet replication engine. And the abstraction is essentially of a replication tree where we have a root node, a set of level 1 nodes, and level 2 nodes. And so when a message appears at the root node, it is replicated across the branches, and then we finally have these copies of the packet. Apart from this, the PRE also supports dynamic pruning of the tree. And this is achieved by associating each node with an exclusion ID. And when the packet comes in, the packet's metadata can be associated with an exclusion ID at level 1 and level 2, which essentially results in a pruned tree like this, where you have the packet copies that you exactly need. And so even though we have this construct, it is not trivial to actually build a solution for Scallop. And that's for the following reasons. So we have the PRE entities like root, L1 and L2 nodes, level 1 and level 2, and the video conferencing entities like meetings and participants and so on. How do we do a mapping between the two such that we are able to achieve multicasting? Second, every meeting configuration can have different mappings that will work for it. So for example, this depends on the rate adaptation status, that is whether the meeting needs rate adaptation or not, how many of the participants need rate adaptation, and so on. Second, the number of participants in the meeting can affect this. And finally, within the course of a meeting, this configuration can dynamically change, making this much harder. And third, the Tofino's PRE actually has limited resources. And so we can summarize this to ask the following research question. How do we first correctly and second efficiently map the video conferencing entities onto the PRE entities for each kind of meeting configuration? So in terms of solutions, we have various optimal designs, each catered to each kind of meeting configuration. But here, and also we can dynamically migrate across the different solutions depending on the current status of the meeting. Here I'm going to give you a taste of one of the solutions, which is sort of the base solution without rate adaptation, called the non-rate adapted design. And here we find that the optimal solution is actually to map the meeting with the root node, the participants with level 1 nodes, and the egress ports with level 2 nodes. And we use pruning at level 2 to ensure that a participant does not receive its own packets. Actually, we can go even further and aggregate 2 meetings into a root node and use pruning at level 1 to ensure that the participants of one meeting never receives the packets for another meeting. And so this design lets us support up to 128,000 concurrent meetings and 2 to the 24 concurrent participants, which amounts to about 16.8 million participants altogether. So now I come to the evaluation. First, we find that Scallop can process more than 99% of the traffic directly in hardware. And in order to evaluate and come to this number, we essentially ran calls using Scallop and found that there are 3 different classes of traffic. And essentially, the parts colored in red are the only ones that go to the local control plane, so the switch agent. Taken in summary, we find that more than 96% of the packets go directly to the data plane. In fact, when we look deeper, we find that more than 99% of the bytes go to the data plane. And this is because the heavier packets, which are the media packets, go to the data plane. And so this way of splitting Scallop into control and data plane is effective in reducing the load on software. Second, we find that Scallop improves the scalability over software by anywhere between 7 to 211 times. So here on the x-axis, we have the number of participants per meeting, and on the y-axis, we have the maximum number of meetings supported by one switch. And we plot 2 different performance envelopes. One is for Scallop, another is for a powerful 32-core software SFU. And so the lower bound of the envelope essentially is associated with the worst case where everyone in a meeting is always sharing and receiving media. And in the best case, only one person in a meeting is sharing media. And so the performance envelopes look like this. Now, at first glance, it may seem like there's a bit of an overlap between Scallop and software. But what this essentially means is that sometimes the worst performance of Scallop is slightly worse than the best performance of software. But given a particular meeting configuration, Scallop always performs much better than software. And so let's take a few examples. With only 2 participants, Scallop gets an improvement of 211 times. With 5 participants in the worst case, that is when everyone is sending and receiving at the same time, Scallop achieves an improvement of 11 times. For 20 participants in the worst case, 26 times. And for 50 participants, where it's extremely unlikely that everyone is sharing at the same time, we consider the best case, which is like a webinar style, where Scallop gets an improvement of 211 times. Scallop also reduces the SFU-induced latency in the median by 27 times and in the tail by 8 times. And so in conclusion, Scallop is a novel hardware-software co-designed SFU where more than 99% of the traffic is processed in hardware, supporting up to 128K concurrent meetings, achieving a scale improvement of 7 to 211 times on software SFUs at a comparable cost, and reducing the SFU-induced latency by up to 27 times. Our artifacts are on GitHub, including a software control plane, a software model of the data plane, and 2 hardware prototypes on the Intel Tofino switch and the NVIDIA Bluefield 3 SmartNIC. So with that, I come to the conclusion of my talk. I'd like to take a moment to honor the memory of the survivors of 9/11, because I come from America, which is my second home, and today is September 11th. And with that, I thank you and open the floor for questions. Thanks.
Questions?
Well, I'm a bit confused with the motivation because SDN is like intra-domain network technology and SFU is an application level construct, right? So why do you really need to go for SDN and implement it in programmable switches? I'm not really kind of buying the motivation. Why would you do that?
So even though SFUs are application layer constructs, the fundamental sort of idea behind SDN, which is that separating the control logic from the actual data plane where the hard work is done or the heavy lifting is done, is what is the motivation here. So that is the idea that we sort of borrowed from the SDN world. So we find that is very useful here.
Yeah, but maybe another way to ask the same question is, usually application on Zoom, they don't have AS. AS is our network infrastructure, right? So they attach their servers to existing networks, right? So, I know, those application layer operators, they don't really have network infrastructure to put these programmable switches to implement this functionality.
Right, that's a great question. So Zoom uses cloud services to get their work done. And our idea essentially is that in the cloud itself, there are switches that are being used, right? So if the cloud providers switch to a model like this for video conferencing traffic, then application operators like Zoom can actually leverage that and use the cloud services still. But the work has to be shifted from the software within the cloud to the actual data center switches that are already present there.
Okay, I will not take more time to explain this question, but yes,
Sure,
I think it's, I don't know,
offline.
cloud providers usually use switches for their like service purposes. They don't provide it to the cloud clients to use their switches. So they provide, you know, virtual machines or whatever. So it's, I don't know. But anyway, we can talk more about with the realistic business model.
Thank you.
Okay, another question, go ahead.
Yeah, thank you. Thank you for the very nice talk. I think, like, if you offload this to the Bluefield, so the Bluefield can do like this minimal function to, I mean, replicate and maybe drop packets. Did you think about a co-design of the data plane with the host, where the host can do then more elaborate function like transcode to different video codecs, or do the maybe the layer adaptation or these kind of things?
Yeah, so that's a great question, thank you. There are two thoughts here. One is that we have been in touch with NVIDIA, and one of the things we find is that they are in the process of enabling bulk replication. So right now, at the time of writing this paper, that was not available, but it's going to come. So maybe there's an opportunity there directly in the hardware of the SmartNIC. Secondly, as you said, there is a possibility that we offload the control plane to the host and do the rest of the work in the sort of ARM cores in NVIDIA, in the SmartNIC. So I lost my chain of thought there, but essentially, we are yet to sort of, we are yet to sort of evaluate the performance of Scallop on that kind of an architecture, where essentially the ARM cores are taking care of the data plane work. So we should have a number sometime soon, but we don't have it yet, essentially. Thank you.
Okay, let's thank the speaker. Yes, thank you. So this concludes the session. The rest of the SIGCOMM will happen at the auditorium downstairs. So no more activity going on in this room.